let's discuss about chemical kinetics. Chemical kinetics is the study of the rate or the speed of reactions. So some reactions are fast, for example, the combustion reactions. For example, the combustion of butane, that's C4H10. So again, this is a reaction with oxygen, and as you know, this reaction will happen very fast. On the other hand, some reactions are slow. For example, the rusting of metal. So obviously, it will take some time for this iron to turn into rust. So again, some reactions are fast and some reactions are slow. And the study of the rate or the speed of reactions is chemical kinetics. Let's consider this sample reaction. We have A plus 2B producing 2C. So here A and B are the reactants and C is the product. Let's say over time, let's say after 1 second, 2 moles of C is produced by this reaction, and at the same time also the amount of A and B are decreasing. So if you base it on the balanced chemical equation, when 2 moles of C is produced by the reaction, 1 mole of A is consumed. So we have a decrease on the concentration of A by 1 molar. This is, by the way, this in unit of molar. So we have a decrease on the concentration of A by 1 molar, and at the same time also, again basing on the coefficients on the balanced chemical equation, 2 molar of B is consumed by the reaction. So again, we use here negative because the concentration of A and B are decreasing over time, because again on this reaction, this A and B will change or will transform to form R2C. So obviously over time the concentration of the product will increase because they are formed over time. Meanwhile, the concentration of the reactants will decrease because they are again transforming to form our products on this reaction. Okay, so over here again, this is at the same time. So after 1 second, 2 molar of C is produced, and then 1 molar of A and 2 molar of B. So there's a decrease on their concentration by this amount. Now let's determine the rate of this one. So do they have the same rate or the same speed based on this equation? Before we answer this, let's go to this example over here. We have two person. So let's say after 1 second, the change in position of person A is 5 meters. Then at the same time also, after 1 second also, the change in position of person B is 10 meters. Now over here, do they have the same speed? So again, this happens after 1 second. So obviously speed is not just about based on time, it's also based on the change in position. So over here, the speed here, that's 5 meters per 1 second, or 5 meters per second. That's the speed of person A. On the other hand, the speed for person B, that's 10 meters per second. So obviously they have different speed, because again the speed is not just about the time, it's also dependent on the change in position. So how about for the reactions? How do we measure the speed or the rate of the reaction? So for chemical reactions, we measure the rate by the change in the concentration of that substance over time. So over here, of course, this one is, so here, the change in the concentration, that's 2 molar over 1 second. So here, the rate for the formation of C here, that's 2 molar per second. Then also on this case, we have 1 molar per second. That's the rate uh, for the consumption of A on this reaction. Then here for B, we have the rate, that's 2 molar per second. So if we see here, they have different rate, because again, the rate is not just based on the time, it's also based on the change in the concentration of that substance in the reaction. Now let's apply this in answering this item. Suppose that at a particular time, nitrogen gas is reacting at the rate of 1.49 times 10 to the power of negative 5 molar per second. At what rate is hydrogen gas reacting? At what rate is ammonia being produced? So again, here we have this reaction, Then ang given is yung rate ng nitrogen gas reacting. So here, the rate of this one is 1.49 times 10 to the power of negative 5 molar per second. Whereas to determine the rate of this hydrogen gas reacting, then the rate at which ammonia is being produced. So we are asked to determine the rate of this reaction. So again, they have different speed because if we interpret this balanced chemical equation here, so again, for every 1 mole of N2 being consumed, 3 moles of H2 is produced is consumed by the reaction. So we can say that the speed of H2, that's times 3 compared to the speed of N2, and then for NH3, that's times 2 compared to the rate of N2. So again, let's use these numbers here to determine the rate of the hydrogen gas reacting. So let's start with the first one, the rate of hydrogen gas reacting, the rate of hydrogen gas H2. Again, here from this balanced chemical equation, we can say that the rate of H2 is 3 times the speed or the rate, okay? That's 3 times the rate of the N2. Again, that's 3 times. The rate of N2 is given, that's 1.49. 1.49 times 10 to the power of negative 5 molar per second. And for this, we need to get our calculator. Again, we have 1.49. 1.49 times, sorry, 1.49 times 10 to the power of negative 5 times 3. So the answer here, that's 0.0047 of, or if we convert this one to a decimal, we have 1, 2, 3, 4, 5. So that's 4.47. 4.47 times 10 to the power of negative 5 molar per second. So that's this. So that's the rate of the hydrogen gas reacting from this reaction. So again, that's just times 3 because that's what's in the balanced chemical equation. Let's proceed to the next one. We have the rate at which ammonia is being produced. So the rate of ammonia. So if we look on the balanced chemical equation, the rate of ammonia compared to N2, that's times 2, right? That's 1. So that's 2 times compared to the rate of N2. So again, that's 2 times compared to the rate of N2. The rate of N2, we have 2 times. Again, the rate of N2 is given, that's equal to 1.49. 1.49 times 10 to the power of negative 5 molar per second. So again, that's 1.49 times 2. 1.49. 1.49. 1.49. 1.49 times 10 to the power of negative 5 times 2. We have 2.98. 2.98 times 10 to the power of negative 5 molar per second. So that's the answer for this one. That's the rate of NH3, and this is the rate of H2. Let's proceed to the next one. Consider the reaction for the production of urea used in synthesizing fertilizers. CO2 plus 2NH3 yields CONH2 2H2O. During the analysis, a student found that the rate of ammonia consumption is 5.45 times 10 to the power of negative 3 molar per second. What was the rate of CO2 reacting? The rate of CONH2 being formed, and the rate of H2O being produced from the reaction. Again, the given here is the rate of ammonia. So the rate of ammonia here is equal to 5.45 times 10 to the power of negative 3 molar per second. So again, the first task is to determine the rate of CO2 reacting from this one. Okay, A, we have the rate of CO2. Now let's analyze our uh, chemical equation over here. The rate of CO2 compared to ammonia. So as you see here, that's 1/2, right? Again, that's CO2 to ammonia. So for every 2 moles of NH3, only 1 mole of CO2 is used in the reaction. So over here, that's 1/2. So again, the rate of CO2 is 1/2 compared to the rate of ammonia. So 1/2, again, the rate of ammonia is given that's equal to 5.45 times 10 to the power of -3 molar per second. So actually merong shortcut here, so just divide this one. So that's 5.45 times, or times, I mean, divided by 2, because again that's times 1/2 is equal to 2 point, we have 3 significant figures. We have 2.73, 2.73 times 10 to the power of -3. So just copy this one over here, molar per second. That's the rate of the CO2 reacting. Next, we have the rate of this one. We have the rate of CO, NH2, and the rate of CO, NH2, 2. Okay, again, the rate here, that's 1/2 parent. So it's the same thing. So it's 1/2 the rate of NH3. So 1/2 the rate of NH3. And this is the same with CO2, right? So it's still 1/2. So I guess we know the answer already. So 1/2, again, the rate of NH3 is 5.45 times 10 to the power of -3 molar per second is equal to 2.73 times 10 to the power of -3 molar per second. That's the rate of this compound being produced by this reaction. Then letter C, the rate of H2O. So the rate of H2O being produced from the reaction. So if you look again here, that's 1/2 parent, right? So that's 1/2 the rate of NH3, and it's the same thing. So we know the answer is equal to 2.73 times 10 to the power of -3 molar per second. So again, to answer this one, just took on the coefficients on the balanced chemical equation. So it's obvious that here the rest is 1/2 the rate of NH3, because here the coefficients of CO2 is 1. It's also 1, then it's also 1. Okay, that's the answer for this item. Let's proceed to the next item. In the industrial production of hydrogen gas, we have this one. The rate of molecular hydrogen being produced is 0.098 molar per second. Again, the rate of the hydrogen being produced, we have 0.098 molar per second. What is the rate of H2O being used? C3H8 being consumed, and CO being liberated or produced by the reaction. Again, A, the rate of H2O being produced. So the rate of H2O being produced. So if we look here, the rate of H2O compared to H2, that's 3/7. So that's 3/7 times, again, the rate of the given. The rate is, we have the rate of H2 or hydrogen gas. We have uh, the rate of H2, again, 3/7 times 0.098 molar per second. Let's use our calculator for this. We have 3/7 times 0.098. We have 0.042. 0.042 molar per second. That's the rate of H2O. Next, we have the rate of C3H8 being consumed. The rate of you have C3H8 being produced. So again, it's equal to, let's compare the rate of C3H8 compared to so here for every 7 moles of H2, only 1 mole of C3H8. So that's 1 over 7. 1 over 7 times the rate of H2. 1 over 7 times the rate of H2. Again, it's given 0.098 molar per second. We have 1 over 7, 1 divided by 7 times, we have 0.098, we have 0.014, 0.014 molar per second. Then lastly, we have the rate of CO being produced by the reaction. So here, the ratio between CO and H2, that's 3 over 7. That's 3 over 7 times the rate of H2. And it's the same with the H2O because they have the same ratio compared to the H2. 3 over 7. Again, the rate of H2 is given at 0.098, 0.098 molar per second. If you solve this one, is equal to 0.042 molar per second. So that's the answer for this item.